Okay, let's dive straight into this explainer and build ourselves a conceptual pyramid of statistics. We're going to literally transform how we understand data from the ground up. If you've ever felt completely overwhelmed by complex formulas or, just wondered how researchers actually prove their claims, you are in exactly the right place. Today, we aren't just memorizing equations. No way. We're tracing the entire evolution of human thought, from primitive counting all the way to the absolute peak of scientific inference. Let's get into it.
Now, this quote right here hits the nail on the head regarding a fundamental human problem. Our natural language, it's honestly terrible at capturing precise realities. Thinkers like Galileo and Parmenides realized ages ago that relying solely on words traps us in this qualitative vagueness. I mean, if I say someone is tall, what does that actually mean? Without numbers, our descriptions are just way too ambiguous to test properly. So the big question staring us in the face is this: how do we bridge that gap? How do we go from vague words to the precise mathematical truth of nature? Well, to uncover the hidden source code of reality, we need a formal system. We essentially need a method to swap out our qualitative ambiguity for quantitative insight. That's what allows us to superimpose these perfect, clean mathematical models onto our incredibly messy, unpredictable material world.
All right, here is our architectural blueprint for today. We'll kick things off with the vagueness of language, build our base with scales of measurement, organize everything with descriptive statistics, meet the legendary normal curve, dive deep into inferential statistics, and finally, reach the summit with t-tests and ANOVA.
Section 1. The vagueness of language. Let's look at how human perception alone totally fails to give us the reliable data we need for actual science.
You see, when we just use everyday words to categorize the world, we're dealing with qualitative data. We're kind of trapped in a primitive state. Human categorization naturally defaults to this nominal vagueness. And the problem is, if we stay at this level, we are completely unable to perform the math required to actually test our reality. We can't find an average, we can't predict probabilities, we desperately need to upgrade our tools.
Section 2. Scales of measurement. To solve this vagueness problem, we've got to build the foundation of our pyramid.
These 4 steps represent an absolutely vital progression. We are moving from basic, sensory-based, intuitive cognition all the way up to highly rational, incredibly precise scientific measurement. Let's walk up these steps one by one.
Step 1 is the nominal scale. Imagine a prehistoric human counting their kids on their fingers, right? One kid, one finger. The numbers here are just labels. They're practically just names. You literally can't add them, subtract them, or divide them. It's like the numbers on the backs of soccer jerseys. Adding player number 10 and player number 12 doesn't magically give you player number 22. It's just simple enumeration.
Next, we step up to the ordinal scale. Picture the finish line of a marathon. Ordinal data tells us exactly who came in first, second, or third. We establish a clear rank. But crucially, it doesn't tell us by how much the first runner beat the second runner. The distance between first and second place could be 2 seconds, or it could be 2 entire hours. We have order, sure, but absolutely no precise distance.
Now we reach a major breakthrough, and that's the interval scale. Think of Fahrenheit temperature. This scale finally gives us equal distances between numbers. The distance between 72 and 73 degrees is exactly the same as the distance between 73 and 74 degrees. This is huge because it allows for sophisticated math like addition and subtraction. Though keep in mind, it still lacks a true absolute zero. 0 degrees Fahrenheit obviously doesn't mean the total absence of temperature.
Finally, at the very top of our measurement foundation, we have the ratio scale. Used all the time in hard sciences like physics, this scale features a true, absolute zero. Think 0 Kelvin, meaning the total, complete absence of molecular movement. This is a real game changer. It unlocks complete mathematical freedom: addition, subtraction, multiplication, and division. The whole shebang.
So the crucial point to remember here is that choosing interval or ratio scales makes your experiments so much more profitable. Moving past primitive nominal and ordinal data into continuous interval and ratio data is what actually allows you to run powerful parametric statistics. It is quite literally the difference between just describing your data and actually unlocking its deepest secrets.
Section 3. Descriptive statistics. Now that we've carefully collected our data using reliable, high-level measurements, it's time to organize the chaos.
Here, we encounter variance, which is absolutely the cornerstone of statistical analysis. Now, don't let the math scare you off here. Variance is simply the fundamental concept of seeing how much our collected data spreads out from the average. We subtract the mean from each score, square it so the positives and negatives don't just, cancel each other out to zero, and then we sum them up. It gives us a concrete, measurable number for the natural noise or spread in our data.
Section 4. The Goddess Normal Curve. To truly wrap our heads around this variance, we have to meet the mother of all statistical tools.
Look at this magical, perfectly symmetrical bell curve. It proves that in the real world, whether we're looking at human height or the natural variance of ocean waves, most data naturally clusters right around a middle average value. The highest point, right in the center, is the most frequent occurrence. And as you move further away into the tails, those occurrences become increasingly, exceedingly rare.
Notice this specific number right here, 1.96. In the world of the standard normal curve, 1.96 standard deviations away from the mean represents a very, very specific boundary. It contains exactly 95% of our data. Anything falling outside this boundary is out there in the rarest 5%. This magic number is basically our bridge. It takes us from merely describing data straight into true scientific inference.
Section 5. Inferential statistics. We are now totally ready to climb to the very peak of our statistical pyramid.
Inferential stats are what save us from scientific ruin. While descriptive stats just organize our data, inferential stats mathematically answer the single most important question in any research: is my finding actually valid? By calculating probabilities, it allows us to confidently state whether the effect we saw in an experiment was actually caused by our manipulation, or if it was just, random chance, just natural variance.
Section 6. T-tests and ANOVA, the absolute summit of analysis. Let's look at the two most powerful tools sitting at the top of our pyramid, designed specifically for that high-level interval and ratio data we talked about. Okay, here we have the t-test. Please don't be intimidated by this formula. It is simply a tool to test the difference between exactly two groups. It was originally developed by William Seeley Gossett under the pen name Student. The t-test basically allows us to infer if the difference between two sample averages is significant enough to represent a true difference in the real world.
Let's translate that intimidating formula into plain English, all right? The numerator, the top part, is literally just the measured difference between your two groups. That's your signal. The denominator, the bottom part, is the natural everyday variation or standard error of the data. That's your noise. Essentially, you're taking the effect you think you caused and dividing it by the background noise. If your effect is much larger than the noise, congratulations, your finding is statistically significant. Now, while the t-test brilliantly handles exactly two groups, what if you have 3, 4, or even more? Well, that is where analysis of variance, or ANOVA, steps in. Think of ANOVA as the heavy-duty ocean liner of statistics. It carefully partitions the variance into between groups and within groups, which lets us handle highly complex experimental designs without completely losing our minds. But remember, both of these tools demand high-quality interval or ratio data to actually work their magic.
And that brings us to a really profound realization. It honestly leaves you wondering, as we reach the top of this pyramid of precision, all the way from primitive finger counting to the goddess normal curve up to the dizzying heights of ANOVA, if we aren't just doing math here. By superimposing these perfect formal systems onto our messy world, are we actually reading the hidden source code of reality itself? Definitely something to chew on the next time you see a statistic. Thanks so much for joining me on this explainer, and keep questioning the data.